another video for an introduction to machine learning. We previously made an overfitting check. Now it's time to compare our models. So questions you might have coming into this could be, how do you use scikit-learn and PyTorch for machine learning? And how do I see whether my machine learning model is doing all right? So here are the answers. We're going to check how our random forest is doing and how our neural network is doing. But first, let's talk about some alternative metrics to accuracy. True positives, or TP, is the number of signal events correctly classified as signal events. False positive, FP, background events incorrectly identified as signal. True negative, TN, background correctly identified as background. False negative, FN, signal incorrectly identified as background. In this terminology, background is considered negative and signal positive. As a bit of an aside, there's some debate as to whether the numbers in the output of a machine learning classifier, such as 0.2 and 0.8, actually represent probabilities. You can read more information in this link. For a well-calibrated classifier in general, these do in fact represent probabilities in the frequentist interpretation. It can be difficult, however, to assess whether or not a classifier is indeed well-calibrated. As such, it may be better to interpret these as confidence levels rather than probabilities. It's then up to a human user to specify the threshold at which something is classified as signal. As such, TP, FP, TN, and FN can be altered for a given classifier based on the threshold. An aside for classifiers in law, Blackstone's ratio is the idea that it's better than 10 guilty persons escape than one innocent suffer. This corresponds to the minimum threshold requirement of 91% confidence of a crime being committed for the classification of guilty. It's obviously difficult to get such precise probabilities when dealing with crime. Let's talk about another metric, precision. It's the number of all things that were correctly classified positive to all things that were classified as positive. Precision is also imperfect. You could have perfect precision by making one single positive prediction and ensure it's correct, but this wouldn't be useful. It's equivalent to having a very high threshold. Therefore, precision is combined with another metric called recall. It's the ratio of all things that were correctly classified to all things that should have been correctly classified. Should have been classified as positive. Recall is also imperfect. You could have perfect recall by classifying everything as positive. However, this would result in poor precision. It's equivalent to having a very low threshold. Therefore, precision and recall need to be considered together. What about metrics for our classifier? Let's print a classification report for our random forest. Here is the classification report for our random forest. It's got 88% precision on the background, 88% recall on the background, 61% precision on the signal, 60% recall on the signal, and it's got 82% accuracy. Now, a challenge for you is to print the same classification report for your neural network. So you can pause this and try and alter this to use your neural network. Once you've done that, let's get the decisions of the random forest classifier. So what we're doing here is predicting the probabilities on the test set using our random forest. Similarly, the decisions of the neural network can be obtained like this. Call it decisions NN. Now let's start talking about the ROC curve. But before we look at the ROC curve, let's examine this plot. We can separate this plot into two separate histograms for background and signal because we know beforehand which events correspond to which type. For real data, this wouldn't be the case. We need to pick a threshold, i.e. vertical line. Once we choose that threshold, everything to the right is classified as signal and everything to the left as background. By moving this vertical line left and right, we effectively change TP, FP, TN, and FN. Therefore, we also change the true positive rate and false positive rate. Suppose we move this threshold from 0 to 1 in steps 0.01. In doing so, we'll get an array of true positive rates and false positive rates. That's what we're doing here. Again, false positive rates, true positive rates, and thresholds for the random forest. The challenge for you is to get the same for your neural network. Call them FPRNN, TPRNN, and thresholds NN. So pause this video and do that yourself. It's similar to the random forest, except that we've changed to decisions NN and called the variables different things. Now we can plot the ROC curve. On the y-axis is the true positive rate, x-axis false positive rate. In the blue full line we have the random forest, and in the orange dashed line the neural network. In grey is a classifier that would just be randomly guessing if an event is signal or background. So the more towards the top left the curve is, the better it's doing. Now we need to decide on an appropriate threshold. In this specific example of classifying signal and background, the primary goal is to optimize the discovery region for statistical significance. As discussed in this link, the approximate median significance, AMS, is the appropriate metric. It's defined here. TPR and FPR are the true and false positive rates, and BR is some number chosen to reduce the variance. Here we'll choose BR equals 0.01. We know you're itching for another challenge, so here we go. Part 1 of the challenge is to define a function, call it AMS, that calculates this AMS using this equation. Call the true positive rate TPR, false positive rate FPR, and BR BREG. Part 2, use this function to get the AMS score for your random forest classifier, AMS-RF. And part 3, use this function to get the AMS score for your neural network classifier, call it AMS-NN. So there we go, you can pause the video and work it out yourself. If you can't work out the first part but need it to move on to the second part, then you can click on the solution to part 1, before seeing the solution to part 2. Okay, we can talk through them. So the solution to part 1 is just the equation here, but be careful of brackets. I made that mistake before. Then the second part is just plugging in the true positive rates for random forest and false positive rates and BR 0.01. And part 3, the same thing for the neural network. Then we can plot. One should then select the value of the threshold, the x-axis, that maximize the MS, the y-axis, on these plots. So somewhere around here for the random forest and somewhere around here for the neural network. That's it for this lesson on model comparison. Key points have been that many metrics exist to assess classifier performance, and that making plots is useful to assess classifier performance. Catch you in the next lesson where we're going to apply to experimental data.